This is my short ISP, the solid-state Tesla coil. This video will cover my various circuits, provide some details about MOSFET driving and half-bridge inverters, and go over the design elements of the coil. A Tesla coil is a type of air core resonant transformer that can produce high voltage arcs and high frequency AC electric fields. The point of a Tesla coil is to take a lower voltage sine wave on the primary coil and step it up to a high voltage sine wave on the secondary coil. Every inductive capacitive circuit, or LC circuit, has a resonant frequency given by this formula. The effect of having an inductor in series or parallel with a capacitor in this type of circuit is a sinusoidal bounce. The amplitude of said bounce is highest at its resonant frequency. In a Tesla coil, there are two LC resonating circuits, the primary and the secondary. The primary circuit can be in the parallel or series configuration, while the secondary is always in the series configuration, capacitively coupled to ground through the air. The sparks, called corona discharge, are created when the charge in the secondary coil tries to make its way back to ground as part of a capacitively coupled circuit. The first driver board created for this project uses a half-bridge inverter made of two 250N power MOSFETs and driven by UCC 37322 and UCC 37321 driver ICs wired in a push-pull configuration across the leads of a gate drive transformer. These MOSFET drivers have an input pin and an enable pin. The inputs are connected to a feedback circuit, and the enable pin is connected to a frequency adjustable 555 timer in a stable configuration. In a half-bridge inverter, two power switches S1 and S2 are controlled by an oscillator circuit, namely the MOSFET drivers. When S1 is turned on, the current is allowed to flow clockwise through the switch, snubber capacitor, and eventually through the load. Then S1 is turned off and S2 is turned on. This makes current flow in the opposite direction through the load and makes the voltage across the load equal but opposite to what it was before. Essentially, S1 conducts when voltage is positive and current is negative, and S2 will conduct when the voltage is negative and the current is also negative. Diodes D1 and D2 are there to dissipate voltage ripples when S1 and S2 change states. Note that the two switches being on simultaneously would create a short circuit, therefore some dead time is built into the MOSFET driving circuit. To drive the MOSFETs in the half-bridge circuit, a pair of complementary UCC 37322 and 37321 MOSFET driver ICs are used. High current gate driver devices are required in switching power applications such as this for a variety of reasons. To enable fast switching of the MOSFETs at a specific frequency, namely the resonant frequency, these gate drivers take in a square wave, process it, and output around 18 volts at up to 9 amps for periods of up to 100 nanoseconds. The 37321 is inverted on the input stage, while the 37322 is not. Thus, the chip's output signals at 180 degrees out of phase from one another while using the same input signal. These chips are extremely temperamental, and if I looked at them wrong, they would just blow up. I eventually figured out that I needed to put some sort of load on the outputs, such as the MOSFETs or a couple of load resistors, because without it they would just oscillate crazily fast and just blow up. The input stage of each driver must be driven by a signal with a short rise or fall time. Thus, the sinusoidal feedback from the secondary coil is fed through an SN74HC14 inverting Schmitt trigger. In the first implementation of this concept, a current transformer was used. The current transformer uses one turn of the secondary coil and around 80 turns of 24-gauge wire to reduce the current coming from the secondary to a more manageable level for logic ICs. The signal is then fed through a high-frequency DC filter capacitor and a 10 kilo-ohm resistor clamped to 5 volts by two 5.1 volt Zener diodes. This feedback circuit was adjusted slightly in the second implementation on my V2 driver board. First of all, the current transformer was scrapped for a simpler antenna feedback system, which uses a high-pass filter capacitor, clamping diodes, and Schmitt triggers in much the same way as the first circuit. The main difference is that I swapped these Zener diodes out for Schottky diodes because of their lower forward voltage drop, and much better performance at higher frequencies. The outputs of the MOSFET drivers, as mentioned before, are connected to the primary windings of a gate drive transformer. The secondary windings are connected to the respective gates of the FETs. The windings are in a 1:1 ratio, which means that whatever signal goes on the primary also goes out on the two secondaries. Note that the two secondary windings have reverse polarity in this circuit. This is to reverse the voltages across the high side and low side FETs, essentially creating a sine wave. Unfortunately, this device was extremely problematic in both driver circuits. Here you can see the signal from the first tiny gate drive transformer, and it's complete garbage. The second one, which I wound myself, produces a better waveform. Unfortunately, neither of these drivers worked, and the only sparks I ever produced were made using the Slayer exciter circuit developed by Steve Ward. The oscillator circuit in a Slayer exciter is typically made of a few key components: a resonant tank circuit, a power transistor, and a feedback circuit. So moving on quickly to design aspects, a couple of CAD tools and materials are implemented in different sections of the overall build. First of all, a secondary winding machine was made out of custom 3D printed parts, wood, and other miscellaneous parts. This winding machine made winding the secondary coil a lot easier than how it would have otherwise been, although it was still super tedious, and I would not want to do it again. The PVC form is mounted to a shaft via 3D printed support, custom designed in Fusion 360. The ends are taped off with electrical tape. Next, the primary bracket is custom designed in Fusion 360 and features 12 vertical shaft with holes in such a way that the secondary winding is guided and supported as it moves down. The primary bracket is mounted on a custom CNC machined aluminum base plate designed in Fusion 360 and manufactured by Argon Prototypes. The function of this plate is twofold. It is a ground plane for stray voltages, and also the MOSFETs may be mounted to it as a heatsink so long as they are attached to electrically insulated thermal tape. Overall, I'm happy with this project, and although I'm disappointed that it didn't work, I really learned a lot.